I will be talking about a way to build non-flag simplicial complexes. So normally when we try to do applications with TDA, we experience several problems. Like for example, normally the applications only utilize the final step of the persistent pipeline. Let's say persistent diagrams or summarizations like persistent images, persistent entropy, or Betty curves and something. But sometimes there are applications that requires to have the whole simplicial complex. Like for example, when you want to classify something over the simplicial complex, like for example, let's consider for example KNN. If KNN is an algorithm that for each point in your data set, you find the K nearest neighbors. So if you draw that, if you draw each connection, you will get a nearest neighbor graph. But if you want to remove all of these restrictions to have only K neighborhoods, only K neighbors and each neighbor to be a point, you will get a nearest neighbor complex. So in that case, you will want to utilize the complex to make your classification using a label propagation algorithm or something. In that case, you will notice that TDA actually has an scalability issue. That means that we actually cannot utilize so many large data. And also, simplicial complexes grow exponentially because they are algebraic and combinatorial objects. That means that they grow exponentially in the number of points and in the dimension of the dataset, of the complex. So in order to address that, what it's done normally is to utilize other complexes, like for example, Vietoris Rips, alpha complex, or with the complexes that sacrifice topological information in order to gain computational efficiency. But because the most topological accurate complexes are computationally expensive to get. So in the other side, there is the RIPS complex, flag and click complexes, like I mentioned, that are very fast to compute because they can be defined only with his one skeleton. So then you have any phase in any dimension automatically because you already have the one skeleton. But in this talk, we want to think about another way to get computational efficiency as well than topological information. So we can present this problem with the game. For example, we have two players, player X and player Y. One of them knows the simplicial complex, but only can answer yes or no. And the other one must reconstruct that complex by asking if any simplex belongs to the complex or not. So the player Y has a maximum possibility of 2 to the power of P questions. So that means that if he can to get the entire complexes asking less questions, it wins. And if not, it will lose. So the idea is how Y can create a strategy that allow him to determine which simplices correspond to the complex with the less number of questions possible. So this talk is about one strategy that can allow that. not with the optimal number of questions, but with the small one. So that's what I mentioned right now. So yeah, now let's start explaining a little bit and required background to understand what we want to share with all of you. This is a haze. This is a haze diagram, which is a cyclic directed graph that can be used to represent any poset or any partially ordered set. For example, if you have a one element set or two element sets and so on, you can use this structure to represent the whole inclusions possible. Using, of course, the set families or the power set of each of those sets. So over those sequence of sets, we can define different orders. Like, for example, lexicographic order, which is the same order that we are we always see in a dictionary, for example. This ordering basically compare elements one by one until one of them is lower than the other. Yeah, and then if we represent that kind of order in the preview, in the reflected haze graph, we will get something like this. Yeah, for each of the families in the previous images. If you notice, it's hard to navigate this graph, and you never know when you have in one point if you cannot discover which is next in that kind of traverse of this plot. So another order is the shortlist order, which take preference with cardinality of elements, putting at the beginning shortest sets, and then for same size sets, it applies a lexicographic order. But this has a very different property. You can see that you never abandon one label until you finish to traverse the entire level. There's a difference here that you never know when, for example, here, when you are in A, you never know when is the turn of visit B, but here is immediately evident. So this kind of order is the same order that we know in a simplicial complex like filtration property. That means that one phase of a simplex always appear before its cophases. For example, if we take any simplex here, any set here and consider like an abstract simplex, we will know that we already visit any phase of that simplex. So we will use this order heavily in this talk. So we all know what is a metric, but here I put it to make clear what are the differences between a Pairwise distance metrics and other kind of metrics that we will see after these slides. Okay. What? Yeah, maybe the name, I should put the other name. But the idea here is to get an example of different metrics that are pairwise. So you can find the real name and put it here, and the idea will be the same. I made a mistake because I do it in the morning. Sorry. Yeah, but thank you. So basically, one of the most important properties of a distance metric is the triangle inequality, which guarantee that 2 points, the distance between 2 points cannot be higher than the sum of the distances between the other 2 points. So an abstract simplicial complex is basically is a collection of sets or subsets that with the property that any subset of any set containing in the complex is also in the complex. Then a phase, any subset of a simplex is called a phase of that simplex, and it is represented with the less than or greater than symbol. And the dimension of a simplex is the cardinality -1, and the dimension of the simplicial complex is the maximal dimension of its simplices. So we also define a collection of q-dimensional simplices, writing in this way. So let's continue and define the check and Reeves complexes. We are in this school, we have been seeing these definitions a lot of times, so I cannot detain too much here. But basically, check requires to evaluate all non-empty intersection between open balls around the points, and the Reeves only take care about the pairwise distance between the elements. So this is an example of the difference between those simplices, those complexes. And one point interesting is that among all different kind of complexes that we can build with on top of our data, at the end they will fall in 2 categories: flag or non-flag complexes. The flag complexes are those that can be defined by the one skeleton, and the non-flag complexes are more difficult because we don't know which simplex belong to that complex, at least that we check it. So that's make them hard. So the inclusion of a simplex in a simplicial complex can be expressed through a predicate function. Basically, you can always compare if the distances employed to construct that complex is higher or lower than a given radius. So we can represent the predicate for the Reeves complex in this way, and the predicate for the check complex in this way. This is the indicator function that evaluates the condition and return 1 or 0 depending of the true if the condition is true or not. Okay, I don't know if you have any doubt, you can interrupt me and ask. Okay, so now let's see what is a generalized distance. A generalized distance can be one n distance, multi-distance, or m metrics. Basically, that means that we can compare a set of points instead of just 2. So there are 5 properties which we list here, and depending of which of those properties the distance hold, that will be the name that the distance is. So that will be the kind of distance that we are talking about. So basically, the multi-distance or the generalized distance is 0 if all points are equal or no pairwise different, or we don't have pairwise different points. And the second one means that we will have the same distance no matter how we permute the points. the third one is called the simplex inequality, which is the generalization of the triangle inequality. And the other one is other kind of properties similar to this one, but corresponding to another distance. We will see this after this job. And this one means that the multi-distance should be always greater or equal to 0. So the n distances satisfies the first properties, and the multi-distance satisfies properties 1, 2, and 4, and the metric satisfies 1, 2, 3, and 4. So we can go back again, and then the three first properties correspond to n metrics. Then the 1, 2, and 4 correspond to multi-distance, and then 1, 2, 3, and 5 correspond to metric. So what is this important? Because we can utilize those kind of distances as a way to measure an end relation between a set of points. Instead of just having information between pairwise, with these kind of things, we can get richer spaces. And another desirable property, which is not officially required, but is useful, is this one, that one generalized distance should be higher than the maximum, that the maximal generalized distance taking one of each points. If you take 1 point and compute the generalized distance, and you do that for taking every point, you should have your end distance higher than that one. Why this property is important? Because, for example, when in flat complexes, that property doesn't hold. That, for example, the end distance is not higher than the maximum of the other distance. That's explain why you can define a flat complex from the one skeleton, because any other high-dimensional simplex will give you a distance lower than his faces, so it's already included in the complex. That's why you can grow a flat complex for any dimension once you have the one skeleton. So that property will be the one that guarantees that your complex will be a non-flat complex. And as you may see, as you may notice, those kind of properties make the distance hard to compute, more harder than a pairwise distance. So here there are few examples of generalized distances. For example, the first one is the maximum multi-distance, which corresponds to the Reeves distance or to the flat complex distance, because once you compute the maximal distance among the one skeleton, that will be the same distance no matter which dimension you want to analyze. The other is the Fermat multi-distance. Multi-cosine is between woods, because this actually has no any, this function has no any geometrical interpretation until now. So any of you that want to try it, it will be for sure a paper in any journal, because that is a mystery. That distance was utilized by Powell Loco and Uwe Wagner in one paper that they published in 2014 to compute, to analyze text data. So they noticed that the cosine function, cosine similarity function, really, in reality, don't, it's easy to extend to any number of points. They do it with the cosine similarity and also with the Jaccard similarity. I didn't put it here because I just want to show how hard is compute one of those multi-distances. So the easy to compute distance will have n dot m complexity, which is n, the number of points, and m, the dimensionality. But it could be greater than that. If the dimensionality of your data set is high, or you have a lot of numbers to compare, that will be a burden for your computation, for you when you are creating the complex. So let's talk about the algorithm that we propose in order to build those kind of non-flat complexes, and what kind of approaches we create when we face any challenge. I will put the challenge, then okay. Basically, when you want to construct a complex, this has you only need to guarantee that any simplex that you want to include has all its phases already included in the complex, and also that the simplex itself makes the predicate that you choose equal to true or to 1. So yeah, this also tells us on another thing. When any of the phases fail to satisfy the predicate, that means that any cophase of that phase will not belong to the complex either. So if we really, on that order that we were talking about at the beginning, we will guarantee that we have a way to jump a lot of simplices that not belong to the complex. That's why we do these kind of things. So the main challenge is that we cannot predict which simplex belong to the complex. We need to verify each candidate simplex and need efficient ways to pruning the data. But what I mentioned before is that if any phase fails, all its cophases already fail, and we don't need to check it. That is a big improve. So we rely on the filtration property to determine that, to guarantee that kind of approaches. So this enables that we can reject a lot of invalid simplices, and we can reduce the search space and also construct our complex with consistency and with the properties that we want to achieve. This is an example about the idea that I'm sharing. Since this is the same Hayes diagram reflecting. The previous one was rotating around the x-axis, but this one is in this position to clarify the idea better. We want to build this complex, which is a phase of a tetrahedron. If we don't create a strategy to check which phases correspond to the complex and which one do not, we will end to checking everything in our complex. But with this approach, using the shortlist order, we can notice early that there are simplices that not belong to the complex, so the cophases either belong to the complex, and we don't need to check it. So we only check in the to know if that simplex belong or not, simplices which phases are already in the complex. Because I don't know if it's clear what I mean. Whenever you reject one simplex, you will never create a cophase, because what you need to build that cophase is not there. So naturally, we create a pruning strategy that we accelerate our process of build our non-flat complex. Okay. So first, our algorithm has two main pieces. The first one is to build one skeleton, and the second one is to expand that skeleton to higher dimensions. But we build the skeleton. This is a very simple algorithm, but it reflects the idea. So the main components are there. For example, we check, for example, elements higher than the others, like here, for example. This means that we know when we have a point, we know that if any other point or any other vertex is lower than the one that we are checking, we know that we already processed those data. I don't know if it's okay, but this algorithm, also you can see here that every node will have a collection of neighbors, because we are building here one graph, but representing that graph at the same time with adjacent lists. I don't know if you have programming a graph before, but you have several options to program in your graph. You can use an adjacency matrix, an adjacency list, an incident matrix, or incident list. So we chose here an adjacency list, meaning that we collect all of those points or all those vertices that are connected with the vertex that we are considering. At the end, we will get the one skeleton, the collection of 0 simplices, and the collection of 1 simplices, but also per vertex, we will have the neighborhood of that vertex. So we will see that applying this algorithm, we will get these 3 guarantees that are easy to see and easy to evaluate, but are important to get the other optimization that we will do for the high dimensional part, which is the more complex part. The first one is the lexicographic order and the simplest expansion. That means that because we configure those 2 cycles considering y higher than a, so this condition guarantee a lexicographic ordering in the one skeleton. So the other thing is that we only need to check the maximal element in one simplex, no matter what dimension that simplex has. That means that if we have a simplex with dimension 100, we only need to check 1 point, the last one. That is a good enhancement. And then the neighbor lists are are sorted increasingly because the way that we insert the points is easy to see here, that every point included will be greater than the others that belong to the list. That has a very good help when we will develop the next algorithm. Then the consistency of the search results. Since our nearest neighbor lists are sorted, we only send data to find in the sorted list of another points in a sorted sequence too. So everything is sorted, and that gives us the property that the searching results will be also sorted. So if we find an element in a list so if we have a list of elements and we try to find in that list the element y, and y is located in position P, we know that the second element that we try to find, G1, will appear in a position P plus K. Always the position will be increased too, because everything is sorted ascendantly. And that is a very good property because this allow us to skip elements that we know we don't need to check. If we don't have this kind of shortcuts, we need, every time that we need to check everything, we need to start from the beginning, every time, from the beginning. So each point also has a last position element, which telling us that we end the last search in the neighbor list was in the position P, for example. And that allows us that any other point that we want to find in that neighbor list will be in a position higher than P. I don't know if it's clear, but this is a very high enhancement because you don't need to search every time from the beginning. Okay, this is those properties guarantee that our algorithm can take a lot of advantages that if we don't notice that, we should have, for example, four loops starting from the beginning and checking simplices again and again. But we don't do that, fortunately. So, for example, to expand one simplex with dimension q minus 1 to a simplex to dimension q, we need to attach this opposite vertex and evaluate the predicate to see if the entire simplex will belong to the complex or not. But how many vertices we need to check, or which are those vertices, because we have in a computer, so we don't know where the vertices is, where the vertices are, or which are those vertices, how to find them. We really need to evaluate the predicate for all points. So basically, the answer of those questions are in those lemma that we see before, because we know that each vertex has a neighbor list, so the only cofaces that vertex will have will be as a combination of its neighbors. Because if we want to connect something to another vertex, it means that this is already a neighbor of that vertex, so it will belong to the list. So we don't need to check either to the entire data set of points, just to the list of neighbors. So if the graph, or if the complex is the one skeleton is sparse, we will gain a lot of speed because we don't need to check the entire data set. Because of the lexicographic ordering and monotonicity, and the order of the list, we know we only need to find candidate vertices greater than the maximal element in the simplex. So we have the neighbor list, and also we know that we only need to check in the maximal element of the simplex. So we are reducing speed for any way that we can. We also know that the candidate vertex should be present in the name list of each element of the simplex except the minimal element. Why is that? Because since you find new vertices considering the first element of your simplex, because your simplex is sorted lexicographically, you know that you need to check only elements higher than the maximal element, so you find those maximal elements in the list of the first element of your simplex. So any element that you find, you need to see if it belongs to the list of the other remaining elements inside that simplex. If not, you know that that element cannot be the opposite phase of that simplex, and you ignore it. So this checking is faster than evaluate the predicate. So with these ideas, we can skip checking the predicate every time that we need to include a point to the simplex. This is assuming, of course, that we have a lot of simplices that will not belong to the complex. So when you have your complex sparse, for example, which is the majority of elements in data scientists, for example, you usually don't get the whole simplex. So everything connected with everything in real life. So the majority of simplicial complexes are sparse. So that means that if we can get a fast way to ignore things that we know that that will not belong to the complex, and remember that every time that we skip one simplex, we also skip the whole possibilities of cofaces that simplex has. So we remove too much things. But there is another challenge. We need to traverse the neighbor list of each element that we want to search. So we need to optimize that too. So, okay. Yeah. So we know that there are searching algorithms, like, for example, binary search and other, maybe not to know, but it's called exponential search. Because the linear search, you need to check every element, so the complexity is order n. But this one just evaluate, since it takes advantage that the list is already sorted, so it start looking at the middle, then it divides and look at the middle of the middle, the middle of the middle of the middle, and something like that, and that's why the complexity is log n. But the other algorithm do something different. The exponential search algorithm find the interval where it's better to perform binary search. So basically, it starts multiplying, and then when it finds an element higher than the target, it will execute binary search in that small area, giving rise to a complexity of logarithm of d, which d is the position where belonging to the element that we want to find, even if the element is not present. So we have a list, a neighbor list, that when we try to find y, it will return a position, even if y doesn't is not present in the list. That will give you the advantage that we want to skip elements, even when we don't find it in the list. So, yeah. Basically, we use the position P, but these algorithms has two different behaviors, but they are very related. For example, the exponential search is better than binary search when elements are accumulated to the beginning of the list. If that is not the case, we will wasting searching time. So that's why we take advantage of our value of the last search. You remember that when we search something, we get the position after which we need to search after that search. So that position guarantee that our list, we cheating. We cheating the algorithm, making a trick to short the list by moving this pivot or this offset. You know, it's like the list starts in position P. So we always have elements in the beginning of the list. So that is another advantage of these things. Any comment or question? Okay. So this is the exponential search algorithm. Is a modification of the original one. Basically, what we modify is that we return a Boolean variable telling if the element is present or not, and the next element is the position where that element should be if it were present in the list. So basically, we verify that the list is not empty and the p-value is valid, And then if the element is in the first position, the position P, then we return the position and true. If not, we find the best interval where the element should have. And then we perform the binary search. This is a binary search where we locate it in the middle of the list. Then we iterate until we find it or not. And with this algorithm, we get a logarithm on the position of which that element should be present. But you should have remembered that we truncate the list with those position P. So this complexity is really small because we are truncating the list. So we are considering points very close to that offset. So this algorithm is very efficient. Okay, but we use that algorithm to verify if a point of a vertex is a candidate vertex to belong to a simplex. So we know that we need to verify if the candidate point belong to each nearest neighbor list. So basically, we iterate for the list and perform the exponential search, and then we update the last position in order to get advantage of that search the next time that we search again. So basically, we have those kind of algorithms are called unnamed output sensitive algorithm because depend on the data, on the data nature, not just the input. When you try to program something, you will always want to get an output sensitive algorithm. For example, if you want checking intersection of something, you want an algorithm that depends on the number of intersections and not of the size of your data set, for example. So this algorithm is order K, which is the order K dot the logarithm of the position where the data should have located. So this is very efficient if the dimension of your data is lower than this log D, which is mostly the case, but it could be. So this is the final algorithm, which is the expansion algorithm that allows to grow our complex to high dimension, no matter the dimension that you want to build. How it works? We first compute the one skeleton. Why is that called naive? Because we use 2 cycles, but for example, if we apply a space partitioning technique, like for example, vantage point tree or Morton curves or Hilbert curves, which are curves that move points close in the real space to be close in the list. Because you have a list of elements, you don't know which element is after you. So you need to check. But maybe the element that is on your side in the space, for example, with the coordinates x, y, yeah, is in the final of the list. So you need to traverse the entire list to check that. So this locality property is very important and make the algorithm way more efficient. So if we apply one of those techniques, we can reduce the complexity of naive skeleton to be from n squared to be n log n, for example, which is a good improvement. But then, when we have the skeleton, when we have the skeleton, we iterate per dimension to construct the next dimension of simplices. So basically, we pick each simplex of the current dimension, which is 1 in this point, and then we try to build simplices of dimension 2. But how do we do that? As I mentioned, we only consider the maximal element of the simplex, so we reset the neighbor last positions, which is the position P here, and then we perform an exponential search to see where is the maximal element in the minimum element list. O sea, we need to find the position in the name list of the minimum element of the simplex where its maximum element is located, which could be the end, maybe the end position. So this maybe I should remove this, maybe. Yeah, but then since we know that we only need to search in the nearest neighbor list, we don't need to check the entire complex. Imagine that you have 100 points and your neighbor list has 10 points. It's a huge improvement. So then for each position, we evaluate the first candidate, which is the element in position P in the nearest list. So only if the candidate is true, o sea, it's a real candidate, only in that case we will evaluate the predicate, which is a very expensive operation. And then if the predicate return true, o sea, the predicate says that this should be a simplex on our complex, so we include it in the next dimensional list. Why we only take care about collections of same dimensional simplices? Because we already have the all phases in previous collections of simplices. So after that, when this while loop finish, we'll update the complex, and then we have our complex complete. I don't know if it's clear, but this algorithm can build those kind of complexes that are very hard to compute in a more efficient way. So we have a few examples. We use here the complex, the cosine multidistance, and then we here compute a data set with very few points, very few samples, but we compute very high dimensions in the simplicial complex and also in the homology, but the homology information I couldn't put it here. I couldn't find it. We also do it with another data set, which is not high, but it presents a curious property, which is that one-dimensional cycles are almost all infinite, which is which may be dangerous when you use distance to compare persistent diagrams, because usually those distances remove persistent intervals with infinite depth. So in this case, you will see that you will get no data because almost all cycles are infinite cycles. That happened because we are using the cosine multidimensional distance, which those distances act like an additional restriction to build high dimensional simplices. For example, in other kind of complexes, since you are really only in Pairwise relations, you have no real constraint to build higher dimensional simplices. But here, besides satisfy the Pairwise conditions, you also need to satisfy the entire predicate. So this is the bibliography that I use in these presentations. So in case anyone is interested in explore more, and that is the talk that I was prepared.
Okay, I think we have time for maybe a few quick questions.
What do you mean? Time seconds? You mean how much time I take to build this? Okay. This is this is still work in progress because it lacks from all topological thing because well to answer I start working in this thing from 2020 for example, 4 years, but it's it's a work that is standby waiting for someone that want to complement what is missing yet because I use it, but I cannot explain the kind of spaces that those multi-distance build. There are only one defined open ball with the maximal distance, which is not much useful because that is the same distance that RIPS use. But the other ones has no defined kind of ball to define open spaces. 4 years, but it's a standby. So sometime in some moment I will publish that, but it's still unpublished. Okay, thank you. Which slide? Okay. Yeah. Yeah, but no show any results here. Less, I tried others, but not the volume. The volume. I just put the volume to make a point that is very hard to compute. Okay. Okay.
Each one they rotated into however many cycles constantly before one. So like that's kind of what happened. They kind of 70%. What very albums.
Yeah. Yeah, but this is, remember that this is a modified thing. It's not exactly the same that cosine. But I know what you mean. And also we need to restrict the edge length because it grows. I didn't show here, but it grows a lot. But yeah, thank you. Okay.
There are like specific real world applications that you had in mind as you were building your algorithm.
Yeah.
Images or I don't know, just like what?
Yeah, my PhD is about classification. Classify that data. You have a data set, a partially labeled data set, and you want to define which is the label corresponding to unlabeled data. But I do that just with TDA. You know that TDA commonly is used as a preprocessing step of machine learning. But I noticed that in the process of getting the persistent information, you already have all relationship between your data in any dimension, in any scale. So then you forgot all of that and then only use the summary. So what we do in our algorithm is look the persistent to understand what will be the best subcomplex that represent that approximate most our topology, and then use that complex to propagate unlabeled points and find labels. So in that process, when I use common simplicial complexes, I usually get out of memory because I have no cluster. I have no cluster, I have not anything. I need to do that in my laptop. So when I got those problems in my laptop, I need to find a way to restrict the exponential growing of those kind of complexes, and that's why I found the paper of Power Loco and Uber Warner and Star, I see that the algorithm that they propose has open improvement opportunities. So I do it, and then I use those kind of things in my own work. But then I just present it because topologically, I have no any information of that kind of distances, and no one knows, because the papers that I show here, no paper of those has real descriptions of anything, and they are very recent. They are papers from the last year, and even from this year. Maybe I cannot put no one, but that is anything that you can do with the complex, you can use one of those kind of complexes. It's like a witness complex. Yeah.
All right. Let's thank our speaker again.